Okay, so if you haven't had a chance to read through this, please make sure that you read through this for Thursday so that you're ready to go. We're going to be doing a four-sided traverse. We're going to be utilizing a total station with a tripod reflector clipboard. The only thing addition that I don't have on here that I told you, you'll be using a plumb bob for your back sights and foresights. We'll be starting at a given point and then we'll run it around. I'll give you a little diagram here and we'll kind of show you how that works. We talked about this the other day, but it's been a couple of weeks, so I just want to re-emphasize this. And when you guys get done, you're going to have stuff that you're going to have to deal with. So you're going to write a report calculating angular misclosure. You're going to distribute the angular misclosure. You've got a starting bearing that you'll be given. You're going to calculate lats and departures, air enclosure, precision. Then you're going to do an adjustment on that with a compass rule. And you're going to utilize that to create coordinates. So the final report, you're going to have a copy of your field notes. Remember, I stressed that a couple weeks ago. Everything we do, field notes are going to be really, really important on this. And you're going to have your coordinate calculations, and I'd like an AutoCAD drawing also present for that. And then the other write-ups that we talked about. So just make sure that you're ready to go and have, you might want to bring a calculator also. So if you wanted to calculate your angles while you're out in the field, that's very helpful. And something to write with certainly. I believe I have clipboards. I'm going to verify that tomorrow, but I think we've got clipboards. But if you need some paper, make sure you bring a notebook because you're going to need that as well. Okay. Let me just flip over real quick. What this traverse is going to kind of look like, it's a four-sided skinny traverse. Unless I change it, I doubt that I'm going to, but I'll find that out tomorrow. But it's kind of a real narrow, skinny thing. Looks kind of like this. And we usually start out up top. This is the top of the hill, and the bottom of the hill will be down here. So we're usually, this is point A, point B, C will be at the bottom of the hill, and then D. And we talked about this, you know, a bit ago, but what you'll do is you'll occupy each station. So if we start at A, we will shoot a distance A to D and a distance A to B. We're going to measure the internal angle. We're going to do that angle a couple times just to make sure it verifies with the 30 seconds that we're giving you. And then once you get that to work, you'll set up a B, and then you'll back sight A, and you shoot the distance A to B, shoot the distance B to C. You'll measure this angle several times. Do the same thing here. We'll shoot this way, and then ultimately we'll close out with our closing angle, shoot this way, and shoot this way. So it doesn't sound like a whole lot of work to do, but guarantee it'll probably take us every bit of 3 hours. You have to do 3 setups, or 4 setups rather, and that takes a while. We got to make sure that we're over the point, leveled up, and that's going to be probably the biggest thing that people are going to have to deal with. If you haven't done that in a while, I'll make sure I show you how to do all of that. Okay. So that's what we're going to be handling, and then we're going to be running on that. We'll be coming back in and dealing with the work associated with it. Okay. So does anybody have any questions on any of this before we move on? Nobody questions? We're okay with that?
I'm good.
I think you'll find it's going to be, it's a real good exercise. The one thing is just keep in mind that your angles are not going to be great. Your distances will probably be better, but you probably won't have a really, really good closure. I think the best closure I've ever had a group get was about 1 in 10,000, maybe 1 in 15,000. So it's not wonderful, but the idea is just to get the experience of how it works as far as that goes. So, all right, no questions on any of that? All right, let's go back to here. So let me get out of this week. So we are at week 6 now. What we started into last week was talking about differential leveling, profile leveling, trigonometric leveling. I want to do a couple of problems associated with that, and then we're going to talk about some distance measurement stuff, and that'll kind of wrap us up. So, like I said, next week, I believe, normally we would be doing lab 2 this week, but since we're behind, I might just scuttle lab 2, and then we'll jump into doing a building layout next week. So this stuff is still going to be important to it. It's going to build up into that. So you should have these lecture handouts. That's what I'm going to finish off with today. I do want to call your attention to the fact that you've got some homework to do. I'm going to work through some of this a little bit with you today, but in chapter 4, there's a problem 14. In chapter 13, there's problems 4, 11, and 13. Now these guys are dealing with taping correction stuff, which I'm going to go over today. So they're a little bit, you have to think about those a little bit. They're a little bit tougher to do. And then chapter 7 is dealing with leveling notes. And we're going to be doing leveling the rest of the time that we're working out there. So you're going to start to see that next week as well. So this will be important to handle between now and next week, because next Tuesday I'll be going over the solutions to these problems first thing. Okay. So, all right. So if that's no problem or no questions, then I do want to move on. And I do want to emphasize, if anybody out there right now that's in this lecture has not taken that test is only open until midnight tonight. And after that, it's not going to happen, or you're going to have to make special arrangements, and you're going to get a test that you're not going to like. Okay. So just word to the wise. Okay. So that's only 4 people that fall under that category. So, all right, let's move on then. Let me pull up PowerPoint. So we talked about leveling, differential leveling, talked about profile leveling. We talked about trigonometric leveling. So I want to show you a couple of examples just to make sure everybody's on the same page with this. Let me get my PowerPoint up and running. If you do have any questions while we're talking about this stuff, please stop me, okay, too. So we did go over this last week, but I just want to do a few problems just to make sure that everybody's good with this. And then you'll have those problems out of chapter 7 that deals with this stuff as well. So differential leveling is what we're going to primarily be using, and we're going to be utilizing it as just either a loop process or as profile leveling. And profile leveling is good because you don't have to do as many setups. The notes, though, get a little bit trickier with that. So the 3-wire leveling, does anybody tell me what 3-wire leveling is about? We talked about that last week. Anybody know what 3-wire leveling is? We did talk about this. Nobody. Okay. Well, this is a way of measuring or reading 3 readings on your level instead of just your middle crosshair. So that's that process is really useful for control, but we're not gonna be utilizing it in terms of what we're going to be doing. So, and trig leveling is where you're actually not measuring elevation, you're measuring a slope distance typically, and other things. So I'm going to go through that here too. I'm going to do 2 problems associated with that. So let's buzz through here. You should know that when you talk about elevation, it is a vertical distance, okay? And it's a vertical distance above or below a datum. And we talked about all that last week. So I'm not gonna go over that, but just make sure you're aware of what we're talking about there. Again, anybody has questions, let me know. So your 3 primary types are differential, steel taping, and trig. We're going to use a little bit of primarily differential. We might do some trigonometric leveling. I might actually have you do some of that next week if we get a chance to do it, or at another time frame, just so you get experience doing it. Who can tell me, of those 3 types, which is the best type of leveling?
Steel taping.
Say that again, Jacob.
Steel taping?
Steel taping is actually very decent if you're doing things like from a, from a real vertical distance from like say bottom floor of a high-rise building up to like 12th floor. Yeah, you can do that very effectively. But there's a lot of things that can go wrong with that, particularly if the steel tape isn't held vertically. Okay. So yeah, that's actually a really good method. Differential is probably your best because it's pretty foolproof if you just make sure you're measuring your setting up your instrument correctly and holding your rod um, vertical. It's just if you were doing like saying getting from that first floor to the 12th floor doing differential leveling, you're going to be setting up a lot of times, like say in the stairwell, coming up through that. So it takes longer to do. So yeah, I would say probably of the two, steel taping it is a good method, but it doesn't work for all things. So that would only work where you have a real nice vertical thing you can drop a tape along, such as a steel superstructure, where they're working on a building. But if you're doing like say from the bottom of a river bank up to the top of a bank of 200 feet up or something, you wouldn't do steel taping. So differential leveling would be the way to go. So it's the best probably of the three. And trig leveling, because it's not a direct measurement type and there's other things that can come into play with that, it's plus or minus. So it's not going to be the best method ever to use. Okay. All right, so let's see, we're going to go through here. With leveling differential type, remember we talked about this last week, running a loop or a line of levels. Are those the same thing? Is a loop, running a loop and running a line of levels, is that the same thing?
No.
Let me turn it on. I'm not sure I could hear you. Did you say no?
Yeah, because with a loop, you run back to the original spot.
Right.
A line, you just
Okay.
work all the way down.
Well, a line of levels actually is a loop if you do it right. If you recall, let me show you the difference. And this is important to understand too, because a lot of people do, well, they'll do both things. It depends on what you got. So technically, the loop is like this. So you're starting at a point and ending at a point. Instead of doing it horizontally, you're doing it vertically. So that would be the classic example of your loop. Let me kill this guy. This thing doesn't always work the way I want it to. So if I have my loop, yeah, these are the, let's say those are the, actually you usually don't see lines like that. Let me undo that. Usually what you would do is you would have a control point that you're starting at. You got another control point, maybe another control point. So what you're doing is you're setting up your level, back sight, foresight, set up your level, back sight, foresight, set up your level, back sight, foresight, and then you loop it back. So this is your classic loop. So it does give you what's called a misclosure. Now a line of levels says you're starting at a known point and you're ending at a known point. So what you're doing is you're running to points intermediate. The triangle's representing my level, by the way. And so that's my setup point. So if you know this point and you know this point and they're in the same system, you do have a loop because you know the difference in elevation between these two and you can determine a misclosure. So this would be an example of what we call a line of levels, and this would be a loop. Basically, they're the same. Now, if this has got a really high precision on it and this has a high precision, this type of level run might be better than this. Okay, so because everything here is going to be dependent on how good or bad this guy is. And if he's off, everything else is off. So again, you can use both methods. We're going to be utilizing the loop the most probably in what we're going to be doing because I have one good bench out there that we use and we always start at it and we come back to it. All right, so that's a good process to understand. Okay, so the equipment that you'll be utilizing, like we talked about, automatic level. I don't know if I even talked about these the other day, but there's what they call a tilting level. A tilting level, actually, the scope will move vertically. You can move it up or down, and you adjust it so that it's exactly horizontal. So that is a very precise type of level, actually. Not what most people use. Automatic levels have a fixed scope, so it doesn't move up or down. It can move left or right, but it can't move up or down. And inside of it, you have a prism that is suspended by Teflon wires that actually is being affected by gravity, and that's what's really producing the level line through it. So they're not actually as good as tilting levels, but they're not as expensive either. So a tilting level, I don't even think you could get them anymore, but the federal government guys that were using very, very precise leveling techniques, they used a tilting level. The newer levels are digital ones, and those are basically reading a barcode on a rod. So these have actually swept the market quite a bit because they're just easier for people to use. We talked about Philadelphia rods, Linker rods. I think you guys have used the Philadelphia rod before, and that's the kind we're going to use. It's just basically a rod that's graduated in feet, hundredths and tenths of a foot. But reading the rod for some people is probably one of the harder things. So we'll see that when we get out there. We won't, like I said, we won't be doing that this week, but we'll be doing it next week for sure. All right, so let's differential. All right, we're gonna just run through an example, but remember what you're doing with this is you're taking backside readings and you're taking foresight readings. And those guys are just basically you're reading vertical distance above what's called your HI and below your HI. So you have two equations, that your HI is equal to the starting elevation plus your backside, and any other elevation is your HI minus your foresight. That's all you really need to deal with. If you have closed loops, then you can also do this equation where you have what's called a misclosure, final elevation minus starting elevation, and that should also equal the sum of the backsides plus the minus sum of foresights. So those two are checks against each other. So we're gonna do a little example right here so that we can see if we're making sure everybody's on the same page with this. So let me grab something here and I'll come up with something to show you this. All right, so from a schematic standpoint, I'm just going to give you some numbers. We're going to run through a real quick example. So let me clean this up. So basically, remember, from a schematic standpoint, if you're looking at a level, this would be like, say, your ground. And I'm stressing all this because it seems really simple, but when I get you guys out there, people just really don't know what they're doing with this. So you're going to level this up. You're going to get a horizontal line of sight. That's called your HI. So no matter where you turn that HI or that scope, you're getting the same HI reading. And then what you're reading here in this case is a back sight. You bring your rod over here and we get a foresight. And that's this reading right here. So all we're doing is setting it up, reading a backside, reading a foresight, moving the scope, getting another backside foresight, and we just continue that trend. Okay, so I'm going to give you guys some notes here, and we're going to run through these. So if you have a calculator, you might want to pull them out, go through this with me, and give me a sec here to set it up. I know this isn't ideal. I'd rather be doing this on a face-to-face board, but it'll work. All right, so from a note standpoint, we have station, which is essentially just an identifier. Then we're going to have a backside column. Then we'll have an HI column. Then we'll have a foresight column. Now we very often have a rod column. We're going to ignore that today because that would be for profile leveling. So we're not going to worry about that. So I'm going to start out with a benchmark A. And we're going to say that the elevation of this guy is 528.00. So that's a known elevation from somebody. You set up at a point, you took a backside reading, and then you turned to a point called a TP, turning point, and you took a foresight reading on that turning point. Let's say we had 423. So at this point, you pick the instrument up, set up between the TP1 and another TP, just an arbitrary point that we shot out there. So we took a backside on the initial turning point 1, and then we foresighted turning point 2, and we had, let's say, 512. I'm just making these up. So then we set up again, and we set a temporary benchmark. So this is called a TBM. So what you're doing is maybe setting that for somebody like in a building. So again, you set up between these two guys. You had a backside of 707 and a foresight of 348. So we set up again, hit another turning point because we're looping it back now. We took a backside reading of 112, foresight reading of 835. Then we set one more time, looped it back. So we had a backside and a foresight. We'll call this 40. Okay, that was our reading. All right, so this is the typical notes that you would see given, but while you're out in the field, you're generating these. So the hardest thing is for sometimes for people to generate these, okay? So that, you're gonna see that as we get out there. All right, so who can tell me, do we have a closed loop? Is this
Yes.
What's that?
Yeah, it's a closed loop because you're moving back to point BMA.
Yeah. So benchmark A is where we started. Benchmark A is where we're ending. Now, if you were doing a line of levels, you might, like, say, start at benchmark A and end at benchmark C. So you would have an actually known elevation of both of those. So I want you to notice also, and this is really, really, really important with notes, because people screw this up all the time, especially when you start putting profile leveling stuff in there. You should always make sure that you got the same number of foresights and backsights. It's impossible to have a different number. So if I have 1, 2, 3, 4, 5 here, I have to have 1, 2, 3, 4, 5 there. Okay, you can't have 6 and 5. If you did, you screwed up something. Okay. Also notice with a loop of any kind, whether it's a line of levels or a closed loop like we have here, you always begin with a backsight and you always end with a foresight. Okay. Say that again, always start with a backsight, always end with a foresight. And what I do to keep these guys kind of in line with each other, I'll put a line through here, and I suggest you guys do that. So you just say, okay, I can't write anything there, all right? So what's the first thing we want to do before we start calculating anything? Anybody have a suggestion? Before you start calculating any numbers over here, there's something that would be really good to do.
You gotta add them up.
Add up what?
Your backsights and your foresights.
Correct. Well, now actually what you're doing is adding your backsights, and then you're going to add your foresights, and you're going to subtract the one from the other. Okay.
Right.
So you're on the right track, girl, for sure. So here's why you want to do that. You don't want to go through and calculate all this stuff if you've got a 10-foot bus. That's ridiculous, right? It's just a waste of your time. So I can determine my loop misclosure real quickly just by summing these. So what I'm going to do is come down here and put a line. I'm going to put a summation count. So what we're going to do is we're just going to add these up, and we're going to add these up. So you guys can check me. I'm going to go ahead and do this. If you guys have the ability to do that too, go ahead and do that. And then we'll see if we agree. Okay, I have for the sum of the back sites, I have 24.63. These are kind of like latitudes and departures in some respect, the way they work. So we consider these also because back sites are considered plus sites. This sum of this is a plus. Fore sites are considered negative sites. In fact, some people call these plus sites and minus sites. So what I'm going to do is sum these up, and those are going to be a negative. So did anybody agree with my 2463? It's doing
Yeah.
that? Okay, good. All right, so let's go ahead and we'll sum the other column up. And I'm getting 24.58. Everybody's getting that same number?
Yeah, I got that.
Yeah.
And these would be negatives, right? So misclosure then is the addition of those two guys with their algebraic sign. So we have this minus this. And what do you get?
0.05.
And it's plus, right?
Yeah, it's over 0.05.
So what that means is you're coming in higher than you started out. Okay, so if you did some kind of adjustment on this, what this says is that you would adjust everything negatively. You would, in other words, you would subtract stuff. And some people actually do adjustments on their levels, just like you do an adjustment compass rule adjustment. We're not going to tend to do that, but it's particularly for construction work. Here's the only thing that's really important. This is what's really important, is this number right here. If that number is within an acceptable tolerance, then you're usually fine. But that would typically not be adjusted. So 5/100ths of a foot isn't bad. Overall, I'm not going to worry about that. Now, if I came in at a 1/2 a foot, then I've got a problem. Okay, so this is telling me I can live with this. So if I'm setting this temporary bench right here for somebody in a building, they're going to be okay using it. That's what that tells me essentially. Okay, so now we need to determine what the elevation of this guy is. So what we're going to do is we're going to use those two equations. So to get any HI, you're going to take your initial elevation plus your back site, and we're going to write that in the HI column. So we have 528 plus 677, and we write that here, and this is 534.77. Okay, everybody agree with that?
Yeah.
So this is the elevation of the instrument. Okay, this is where the instrument is sitting at this point. The instrument is sitting between the benchmark A and turning point 1. And what we've done is we've established that line of sight through that instrument as an elevation of 534.77. So now we want to determine the elevation of the turning point. So what we do is we take this number and subtract that from it. And that's what that's essentially saying. It's a negative. So I've got to subtract 423, and I came up with 530.54. Anybody agree with that?
That's good.
So at this point, the instrument was between these two. Now you picked the instrument up and you moved it to a new location. Now it's between turning point 1 and turning point 2. So you're taking a back sight on this guy, and this is where we get the term turning point. Turning point is any point that has both a back sight and a fore sight taken on it. Okay, so actually in a loop, every point is a turning point, because if you notice, we started at A with a back sight and we ended with A on a fore sight, so it's also a turning point. So it's impossible to have a closed loop where you don't have back sights and fore sights on every point. So because we are between turning point 1 and 2 now, we have to establish the new HI. So we just use this same equation. HI is going to be equal to that elevation plus the new back sight. So we have we're going to add to this now 745. If you guys verify for me, I think I'm okay. 537.99 is what I'm coming up with. Everybody agree with that? we now turn the scope and we subtract from that our foresight reading of 512. So we have minus 512, and that gives me the elevation of that turning point is at 532.87. So essentially, just think what you're doing is you're transferring elevation from one point to the next point to the next point. And notice the trend right now is we're going uphill. So that means at some point we're going to have to start going back downhill. And we'll see that happen in our notes. That'll be reflected. So now, since we've established the turning point elevation, now we pick up the instrument and we move the instrument between turning point 2 and temporary benchmark. So again, establish a new HI by taking your elevation plus your back sight. And we have, you guys verify with me, I got 539.94. Establish my temporary benchmark now. I can subtract 348 from that. And this gives me 536.46. Okay, so that might be the one that those guys are really after. If you're shooting it for a sewer crew or something, they need that number. So now I set up again between here. So now I'm going to set up, I'm moving my instrument now from between the temporary benchmark and the TP3. So we're going to add now this and this together to write it here. This gives me 537.58. We're going to subtract from that the 8.35. This is now, notice it's starting to go downhill, which it has to. So at some point, if it keeps just going uphill, now in a line of levels, it could, because your one elevation of your bench could be higher than the other. All right, so we did one more setup between TP3 and benchmark A. So we need to establish the new HI. 529 plus the 2.22 gives us 531.45. And ultimately, then we're going to subtract this, and this will be our verification. So notice we are at 528.05. So what you're doing, you're going to take this guy, bring him down here. So you take your final value minus your initial. This is going to give me 0.5. These numbers have to agree, both in terms of sign and magnitude. If they don't, you did something wrong, okay? That's your process when you're doing profile leveling notes. Now, the bigger issue is when you're out there is where do you set the instrument up and getting your readings. The notes themselves are pretty easy to do, but I taught this class so many times, and I can tell you, you guys will be out there and we'll still have problems with levels for weeks. It just seems to go that way. Does anybody have any questions on this?
No, it seems pretty straightforward.
It is straightforward, but again, it's a little different when you're out there in the field and you're looking out there in a site and you're trying to figure out, okay, where do I set my level? Where's my backside? Where's my foresight? It's not as straightforward, okay? So the notes themselves are easy, and the math is easy. There's nothing to it, but really putting it all together, and we'll see that, okay? I know that. Well, we're gonna have issues at first. And when we start throwing in rod readings, so if I put a rod column in here and I start putting that in, that opens up a whole nother issue. So this was just simple. We didn't have that, okay? But we'll get there, okay? We'll get there. No questions on that before we move on? That was stuff that you should have done. I'm sure you've done it before. That shouldn't have been an issue. Okay, let's go back then. If there's no questions, I'll leave that up. So one thing right now, chapter 7, there's 2 problems in there you should be able to do, problems 20 and 22, okay? So try those for next week, because we'll go over those things first thing next week, All right, so those are just level notes, and he's got them written out in the book. So you just basically copy them over, and I think they're both just loop problems. One might be a line of levels, so you're gonna have to do that differently. All right, let's go back and continue. Okay, so basically, again, just 3 equations, essentially, or 4 if you want to look at it that way. You know, HI is your elevation plus your back sight. Elevation is your HI minus your foresight. And then misclosure, you can calculate it 2 ways. You should do it 2 ways because these guys have to check. Okay, if they don't check, you won't have that availability. Now, these equations right here, where it says misclosure is your final minus your starting, and your sum of your, that's not going to work for a line of levels. Okay, if you have a line of levels, when you subtract the final elevation from the starting elevation, what you get is the difference in elevation between the 2 benchmarks. But that is your misclosure, essentially. If you're coming up with one that is different than what the published height is between those 2, then that's your misclosure. So you can still utilize it. For sure. All right, so there's what we just went through. Those are your level notes, and then this was that little example that we don't. That's the one we just did. Although I changed it so we had a little bit of a bust, because this one doesn't show us any bust in it. So we just did that one. All right, so profile leveling. Again, we talked about this, but I just want to reiterate it. This is really good for doing stuff where you don't want to set up like between every stake, because it could take you hours to do that. So this is just a way of kind of cheating, if you will, so you don't have multiple setups. But what you do end up getting in these notes are rod shots, and some people refer to those as intermediate foresights. But they're really highly useful for doing grade stakes. In other words, providing grade for, like, say, a linear alignment, like a highway or something, where you're literally putting a stake in every 25 feet. So you can imagine if you have 5 miles of pavement you're putting in and you're going to stake every 25 feet, that's a lot of stakes. So you want to minimize your setups when you're doing that kind of grading. So this is an example. We went through this last week also, but this is an example of a level loop. Well, actually, it's not a loop. What kind of loop? What kind of loop is this? Or what kind of leveling this process is this?
This is a line.
Right, and you can tell that because you're starting at benchmark A and ending at B. So notice when you sum these guys off, you're off 2.56 feet. Well, that would be a problem. If you did that in a closed loop, you'd have an issue. That means you've got to rerun it. But what this is showing you is the difference in elevation between the 2. So to proof these notes, you take your starting elevation that's published and your ending elevation that's published, and you subtract it from what you came up with when you ran it, and there's your actual misclosure right here. So that's more like it. You know, you got 300ths. So that's good. Also, and I think I mentioned this, when you do these kind of notes, you ignore this column completely until you're done getting all of your HIs, okay? If you try to calculate HIs between rods, if you calculate all this stuff first, you almost universally will get it wrong, okay? The thing to keep in mind here is that while we're doing it, you're actually set up between benchmark A and turning point 1. So all of these guys were intermediate to those, and you weren't setting up, you were just shooting it from the same HI. So all of these rod readings over here, that 9.3, that 6.5, those are actually being all read from the same HI. So you just subtract each one of those from the same HI respectively. And I can guarantee you, people will do that wrong. They'll take this minus that gives me this, and then they'll subtract that from that, and that from that, and that from that, and that just, yeah, that doesn't work. So this is showing you what you should come up with. Again, we went through this last week, and we'll be doing this more and more as we get out in the field. All right. Any questions on those kind of things right there?
One quick question. How did you get the misclosure again to be 0.03?
Okay, so let's go back to that. the way I got that, and the thing you got to look at is that is based on published information. Okay, so what I mean by that is if I'm using benchmarks, what that means is
Oh, I get it.
somebody produced an elevation for them. Okay,
Yeah, and then you
so it
subtract.
might be the county, it might be the city. I mean, around here in Hamilton County, we have 3 different types of benchmarks you can encounter. There are county benchmarks that were established, and then there's city Cincinnati benchmarks, and then of course you have also federal government benchmarks. So they're not necessarily on the same system either, even though they should be. So what I'm saying is, if you found the benchmark out in the field, like this one, you went to some agency and got that number from them, okay? And same thing with benchmark B. I got that number, and that number happened to be this right here, that's 363.1, okay, 01. So these are published. The 360.48 for benchmark A was published, and the benchmark B was published at 363.01, okay? So when I ran my loop using my numbers, I started with the given benchmark, took the backside, calculated an HI, then foresight, and I just did that all the way down. When I ended up at benchmark B, I ended up with an elevation of 363.04, okay? So when I compare that to the published, in other words, I subtract what I came up with, 363.04 minus published 363.01, that's my misclosure, okay? So the bottom line is I'm getting those information from somebody else. Does that answer your question in a roundabout way?
Oh yeah, yeah.
Okay. And again, this is a really good point that I bring up. You have to make sure if you find 2 benchmarks out there that you know that they're in the same system, because there are different systems out there that people have used over time. And there's a what they call a NVGD 88, 1988, and then there was one earlier than that, 27. So those guys, or 29 rather. So you had 1929, we had a system of benchmarks, and then they redefined mean sea level in the 80s. So there are benchmarks that are published in both values, and they haven't all been updated, okay? So you gotta really, really be careful when you do that, okay? So yeah, that's how that works. Any questions? Any other questions then? So we're going to see that more and more. We are going to be doing profile leveling, but we're not going to be going from one bench to the other. We're going to be always looping back. So it makes ours a little bit more simplistic. You don't have to worry about having 2 elevations to deal with. All right, so let's see. Let's move on if there's no questions. So we talked about 3-wire, and of course 3-wire we said was just a way of doing very precise readings. So the cool thing is it keeps you from making mistakes ever, and that's probably one of the big issues that a lot of people have with running any kind of levels, is making simple mistakes in terms of the elevation readings, or your rod readings rather. It's real easy to do. It's real easy to make a mistake. So you got to watch it, and this is what this keeps you from doing. And in this process, you just read the 3 readings. There's an upper, middle, and a lower reading. So you just read them all 3 at the same time, add them together and divide by 3. And the average of those 3 should agree with the middle reading within plus or minus maybe 1/100th of a foot. And if it doesn't, then you got an issue. The other thing you can do with 3-wire leveling is nice. So I've talked about the fact that you typically want your distance from your level to your back sight and your level to your foresight, those should be equal to keep errors from happening. And you can do that with this process because you take your upper reading level number minus your lower reading, and you multiply that by the stadia constant, which is 100 feet in most modern surveying instruments. And that'll tell you the distance plus or minus a foot. It's about a foot, maybe a foot and a half off. So it's not perfect, but it just gives you an idea that you're close. The idea is that you're close. You don't want to have a 50-foot back sight and a 200-foot foresight. That would be a real problem. If you're within, let's say if you got a 150-foot back sight and 170-foot foresight, that's pretty close. That's not going to be as much of a problem for you. That's what Stadia does for you, and that's what you can do that with 3-wire. Okay, so trig leveling. Let's take a look. We're going to want to run a little sample problem with you on this one too. But this is, as we've talked about, this is a case where you are not using a direct reading of elevation. You're measuring it indirectly. So when you hear the term indirectly, what that means is you're measuring something else to get the quantity that you're actually after. So in this case, we're actually measuring using a total station. We're measuring a slope distance, and we're measuring a zenith angle typically, and then you'll have an HI and you'll have a rod reading. So there's a couple of equations. Notice that we have the vertical difference is equal to the slope times the cosine of the zenith angle. So you'll be using a zenith angle. And most total stations actually give you the vertical difference. So you don't even have to use that equation, because you can just look on your total station. It'll say your vertical difference is plus this or minus that. So then you really are just using that equation to calculate an elevation based on a starting elevation, an HI, a vertical difference, and a height of rod. So let me let's see, I've got a problem here. Okay, I'll come back to that in a minute, but this is the type of instrumentation stuff that you'd be using: a total station, tribrac reflector with prism pole, and then usually a folding rule, engineer's rule, so that you can get elevations or distances essentially on that. So let's look at an example of this, and I want to flip over here. Let's see. So we'll go to this guy again. Let me go ahead and delete this, and we're going to generate. I want to do a couple problems here with you. So let's look at a problem here. So let's assume that we're sitting like this. We've got our total station set up here. And we have a rod down here. And this rod has an elevation of 5.62. And this is our elevation starting point. We're at 800. We want to know what this guy is right here. That's its elevation. So you set up your total station and you measure with that engineer's rule an HI. Let's say you measured 5.11. Now you'll see this is actually pretty sketchy, because you can't measure that distance perfectly vertically from that center of that scope down. You have to measure it from the side of the instrument. So it's kind of like you're coming that way. And that's really kind of measuring a hypotenuse as opposed to a vertical distance. So when I say this method is not that good, here's one of the answers that's probably not that good about it. So we get it leveled up and we shoot a distance here. And let's say this distance was 502.62 feet. Okay, so we're pretty far down. And we got a zenith reading instrument, so we're reading a zenith reading value like this. And let's just say it's 102 degrees, 12 minutes, and 32 seconds. Okay. So first off, when you look at this, we're looking downhill, you can tell, but if you look at this number, this also tells me that I'm looking downhill. Does anybody know why? That's it's 102 degrees. So what's that saying?
That's in the
South.
90 would be straight, 102 is below 90. So
Say that again.
90 would be like your horizontal line.
Right.
So
Right.
that's turning over 90.
Correct. Correct. So if you're looking 90 degrees, you're looking along what's called the horizon. And you would also be looking at this horizon at 270. Okay. Yeah. So because this number is greater than between 90 and 270, it's a downhill, okay? That's not going to change anything in our equation, but it just means we have to deal with it. So the first thing we're going to do is calculate a vertical difference. So if we go back to that equation, remember it said vertical difference is your slope, which is 502.62 times the cosine of what? What do we use there?
The zenith angle.
Zenith angle. So we can just read this direct. Now, here's the thing. Remember what I just said. A modern total station is going to do this for you. You don't even have to do this. I think I indicated when we got one of the first total stations, in fact, we had one of the earlier ones in the city, actually, one of the earliest. It didn't do that. So we had to write all this down and calculate this. So if I go through and do the calculation there just to show you, I got 102, 12, 32. And I'm going to take and multiply that times my slope, 502, 62. My calculator gives me a negative value of 106.29. And I'm not going to call it anything better than that. So that's what is that number actually reference? What is that telling me?
That'd be the difference between your elevation and the next elevation.
Okay, so are you saying from this point here to that point there?
Yeah, so it'd be the difference between the two.
That's actually not true. It's actually the vertical difference between the optical center of the scope and the optical center of the reflector. You see the difference?
Yeah, that's why you minus the rod at the end.
Exactly. So, well, what's happening now? Let me qualify this. If this number HI and this number rod were exactly the same elevation, then what you said would have been true. But because they're not, we have to measure those. Okay. So to get the elevation down here, we simply say, and we'll just call this B. So if we want the elevation of B, we're going to take the elevation of where we're sitting on plus that HI. We're going to add to that the negative 106.29, and then the rod is always a negative. So in this case, we do that, and there's our elevation. Let's see what we come up with. We got 800 plus 5.11, which basically gives me the HI of that instrument, minus 106.29 minus 5.62. And it gets me an elevation of 693.20 feet. And that would be, again, it's not going to be perfect, okay? You've got a problem. I mean, you could have errors in those. You could measure that wrong. You could measure that wrong. So you really have 4 things wrong, plus you could calculate things wrong, okay? So
Why do you add the height of one station and subtract the height off of the prism pole?
Okay, look at this logically. Do you see I'm sitting here? Can you guys see this little thing moving around?
Yeah.
Okay, so you see I'm sitting right there at 800, right? And then I add to that 511, and that gets me up to the center of the scope. You see that?
Yeah, I see it.
Okay, so now basically, if I drew a line like that, you're sitting at that elevation, right? So if I drop down this amount, that's this number, 106. So if I subtract 106, that's giving me the height of the prism. Does that make sense?
Yeah, I understand now.
And then I'm going to subtract. So logically, do you see how that works logically?
Mm-hmm.
It works pretty cool, doesn't it? It's actually a really neat thing. So that's actually a really good little thing that you can do there. Okay, and it's pretty simple to do. But again, there's a lot of places for mistakes. So Again, a lot of layout people use this because it's quick. It's real quick. It's a lot quicker than setting up a level. And if you're good with setting up your instrument and doing all your measurements and everything, this number should be pretty good. I mean, it should be maybe plus or minus 1/100th of a foot, which is fine for doing, you know, most construction work. But if you just blow one thing, if I measured this wrong, or just think about this, if I measured that wrong and it's actually 5.5 feet and not 511, what's true about every number I've calculated there?
All those are going to be wrong.
Everything would be wrong by almost what? Almost a half a foot, right? So that could be a problem, okay, if you're doing certain types of stuff. And unless you're doing checks, now I could shoot a benchmark and I could shoot another benchmark. I could verify that. But some people cut corners and they don't do that. They just, you know, it's not that they can't do it, they just forget to do it, or they just think, you know, it's working, so I'm okay. So we always have to be really careful how we do things. Okay, that's kind of the bottom line. All right, anything, questions? Any other questions? Okay. All right, so that's leveling, and so I think we want to move on now. I want to talk about some distance issues. We talked about this, by the way, last week, where we talked about some of the errors associated with leveling. This there, curvature of the earth and refraction, those are usually not an issue if you do what? What's the main thing about this, if you guys recall from last week we talked about? Why is this not an issue typically?
You wouldn't, if you don't measure a certain distance, then you won't have to worry about it.
Correct. I mean, you have to measure probably like 500 feet in both directions before you even start to see it. And to be honest with you, if you've ever looked at a level at 300 feet, it's really starting to get hard to read that rod. So if you're pushing it out 500 feet, you have to have really, really good optics. And most of our instruments just don't go that distance. So yeah, you usually don't have to worry about it because we have shorter shots that we're using. The other thing is, if you balance your back sights and your foresights, if you keep them about the same distance, then this error just drops out because it's negative in one direction and it's positive in the other. When you add those two errors together, they just cancel out. So that's probably the biggest thing you can do from a leveling standpoint to make sure you don't have those issues. Okay. All right, so we talked about some of that. Let's get into some distance stuff. So we're going to look at horizontal distance, and I really want to talk about two things here, primarily taping, which we're not going to be doing a bunch of, but I do want you to appreciate a couple of things about taping, and then EDM work. Okay. So when you hear the term horizontal distance, that means that you are measuring that distance or projecting it to a horizontal plane, and it is used extensively in any kind of layout work, because any set of plans that you use or you pull up, you know, you get a set of working plans on a highway or a floor plan or a parking lot or any of that stuff. All those distances are horizontal, even though it doesn't say that to you. Okay. But you're working out on sites that certainly aren't horizontal. So you're measuring a lot of slopes sometimes, but you got to make sure you're providing horizontal. So that's kind of be really important. All right. So again, let me emphasize that when you see a set of plans, even though it doesn't say that, all those distances on there are considered to be horizontal. So like a building footprint, the information on that, or highway, pipeline, any of that stuff, it's all horizontal distances. So get used to that. So providing horizontal distance is also going to be important when we lay out stakes. That's the other thing we're going to have to deal with. Vertical distance, you know, that's measured above or below a plane, and we use leveling to do that. So we're not going to be doing that too much. Slope distance is cool because it's more convenient very often to measure your slope distance and convert it to a horizontal or a vertical. So particularly horizontal, we use that all the time. So when you're using an EDM or a total station that has an EDM in it, what you're actually measuring is a slope distance, and it's actually giving you a horizontal distance via a calculation, which we just kind of looked at. So we'll take a look at that here in a minute. So two things also when we talk about distance measurement. You can do what's either called measurement or you can do layout. So measurement says that you want to determine an unknown distance between two fixed points. Okay, and layout is where you are setting a point from a fixed point in a known distance. So let me draw a real quick diagram about this, because we've talked about this as well, but we're going to start to see this over the next weeks. This is going to be a really important concept, and it's going to be important for you to know the difference. So what I'm saying is, in the first case, let's say you have a line that you're measuring out there, and you go out and you find some kind of monument here and some kind of monument here. So you want to know what that distance is between those two. Okay, this is a measurement problem. Okay, so we are measuring, we're determining an unknown distance between two fixed points. So this guy's in the ground, he's fixed, and that guy's in the ground. Now the other process, which we do in layout a lot, we come from a known point. So we've got a fixed known point, like a control point, that's a known point, and we need to set a point right here. Let's say that's a building corner, that doesn't exist. So this point doesn't exist, but what you do know is you know your distance, and typically, of course, you'd also need to know your direction. So by knowing this primarily and that, I can go out the exact distance I need to and at that direction, and I can set that point. This is a layout problem. And because this class is essentially advanced surveying and construction layout, that's what we do a lot of. But we don't do it exclusively. So we're going to do measurement and we're going to also do layout. So you need to understand the difference between the two. And when we're measuring distance, horizontal distance, this is a horizontal distance, and that's also considered to be horizontal, right? Or what we need to do is provide horizontal distance. All right, all right, so, you know, your primary methods, you can pace. If you know your pace, you can get a quick idea where you are within 5 feet. That's a good way. Odometer, tachyometry, which is something called stadia. Nobody uses that anymore, but we use it quite a bit at one time. So your primary ways of getting distance are steel taping and electronic distance measurement. Now, you can get GPS-derived distance, but understand what GPS is doing. GPS is not giving you a distance between 2 points. It's giving you a coordinate at the end point of each point. And so basically you can get a distance by doing an inverse. So that's a little bit different. That's not a pure and applied distance. It's a coordinate value that you're deriving from. All right, so let's take a look at some of these. I'm going to skip those. We don't need to talk about those. So distance measurement by taping, and you guys have done this. This is direct measurement, and it's very, very often used to measure horizontal, vertical, or slope, but primarily it's used for horizontal distance. So because of that, that means that you have to make sure that your tape is horizontal. So we'll be utilizing this quite a bit. We won't be using it too much for vertical distance, and slope taping is really pretty difficult to do unless, now you could have a pavement that's really flat, that's on a slope, and you can lay this tape down on that. That's actually a very good way. You could slope tape, but we will probably be using the horizontal distance the most. So with the tape, what you're doing is just applying a known length of graduated tape directly to a line. And this does, of course, require a very precise technique to get it right. There's a lot of errors associated with taping, and I want to show you some of those today mathematically. If it's done right, it yields really highly accurate measurements. In fact, before the advent of EDMs, they did a lot of taping. Now, they also did other things where they had graduated bars and stuff. The federal government did all kinds of things before they had it higher level of, instrumentation, but taping could yield very high accurate measurements, but it had to be done just right. And you had to look at all the errors associated with it, and you had to do it several times, and then they would average it. So again, we're construction, we're not going to be that, taking those kind of measures. Okay, so what we would be using for any steel taping exercise is typically 100-foot steel tape, a surveyor's tape. They are made of several different materials. Now, if you're doing anything accurately, it has to be a steel tape. There is another type of tape called Invar, and Invar is a very highly accurate tape, but you don't want to use it on a day-to-day basis because it's probably about 10 times more expensive than a tape, surveyor steel tape. But it's made out of an alloy, and that alloy doesn't expand or contract very much with temperature changes. So it's fairly stable with temperature change. And most people, if they use Invar tapes, they use them as a standard to standardize their other tapes. So these just are not used out in the field. Fiberglass are a way of just doing a very quick measurement. They're not going to be as good as a steel tape. So people, if you're just want to get a generalization of where the 25 feet is plus or minus a half a foot, fiberglass is great. 2 plumb bobs, because you need typically 1 on each end. Tension handles, if you're actually going to pull up the proper tension, hand level, thermometer, all that kind of stuff. That's all. You guys have seen this before. Now, we're not, one thing, let me qualify, is we're going to be primarily using our EDM total station for measuring distances, but anything under about 50 feet, you can steel tape quicker, and it's probably more accurate than an EDM. So we'll keep our distances fairly short if we're going to steel tape, but we will be doing some steel taping because it's, like I said, it's just quicker than shooting everything with an EDM, as you'll see when we get out there doing this stuff. So if you're taping a horizontal distance on level ground, that's fairly easy, but if you're doing it on slope ground, then you have to break it up into horizontal chunks. Okay, and you guys have done this. I know you've done that exercise. We talked about this. So you have to use these 6 steps. You have to line it in, you have to apply tension, you have to plumb it, mark it, read it, and record it. And all of those things have to happen pretty much at the same time. And lining in refers to keeping it on track horizontally. Applying tension, you have to make sure that you're maintaining a certain amount of tension. Usually depends on the tape itself, but normally anywhere from about 12 pounds to 20 pounds is what people use. And that doesn't sound like a lot of tension, but if you actually put a tension handle on a tape and see what 12 pounds is like, it's actually pretty much when you're actually trying to tape. And all this thing, plumbing is probably one of your worst issues, because that's just got a lot of random errors associated with it, and not everybody's good at using plumb bobs. I think you guys have experienced this, so you know what I'm talking about. So we talk about the lining in process, applying tension, plumbing, all of those, again, they have to happen at the same time. All right, so there's a lot of errors that are associated with taping. You could break it down into just like any type of error that you're talking about with any measurement. It can be referred to as an instrumental error, a natural error, or a personal error. So an instrumental error is an error that is associated with the instrument itself. In this case, if you have a steel tape that you are using, it may not be graduated at the exact length that it says it is. Now they're supposed to be. So if you buy a steel tape, you assume that it's exactly 100 feet, but that the manufacturer doesn't always just guarantee that. So you have to have it calibrated truly if you want to know the exact value. Now, a lot of times you may have a defect in the tape. So what that means is you go out with a steel tape and you break it, and they break really easily. A lot of people will splice them back together. And if they don't do a great job on the splice, that can be a problem. Steel tapes, by the way, and I'll point that out, they do break really easily if you get a loop in them, so we really have to watch that. Natural error is usually occurred by something outside of the instrument itself or a person. So things like temperature change is going to vary that steel tape. The weight of the tape has an effect because that pulls that tape into a shape that looks like a parabola, or what they actually call a catenary. So those are examples of natural errors. I'm going to look at 2 errors associated with taping today for you guys. We're going to look at an instrumental type of error and a natural error. Now, personal errors are a little bit harder to deal with because usually we can't really determine that they've occurred, but they're caused by carelessness, just not being very good at what you're doing. Reading the tape, certainly people will transpose numbers. Or plumbing is probably one of the biggest sources of error because it's just so hard to do. And I've been out on days where we were steel taping and it was just so windy, the tape would be picked up in the wind and it's just vibrating the tape and our plumb bobs are swinging, and those were always horrible days to kind of do any type of distance measurement. So these are the personal errors are errors that are going to be hard to get rid of, and they typically fall under the classification of random errors. And we talked about systematic errors, and natural errors and instrumental errors can typically be systematic, which means that we are going to be able to get rid of them. So I'm going to show you a couple of techniques to do that. All right, so the first one is a systematic error known as the incorrect length of tape. So tapes are not guaranteed to be exactly the value that they say when you buy them. So you can have them calibrated. You have to send away, usually like the Bureau of Weights and Measures, some calibrating company that will tell you exactly what the distance is between the graduations. I would probably say no surveyor I've ever done probably did that, but I would say probably federal government, those kind of guys do. But what this allows you to do is calculate a correction that you can apply. So if you've got, for instance, if you've got a steel tape that's says it's 100 feet between graduation marks, and it's really 100.02, every time you're measuring with that thing, you're getting a distance longer than you actually say you are. So if you go out and you measure 200 feet with that tape, you actually have 200.04. So that's an example of this type of error. So this correction says that if you know how much the actual tape is versus what we call the nominal length, then we can determine a calculation or a correction, and we can apply that correction and solve its value. So in this equation, C sub L is your, let me see, okay, that's going to blank out. C sub L is your correction for length or incorrect length. Little l is your actual length, and L prime is what they call the nominal length. So when you hear the term nominal, what that means is that's what the tape says it is. So if you buy 100-foot steel tape, that nominal distance is 100 feet, but the actual distance is it's calibrated based on. Good example of nominals, when you go buy 2x4, it's not exactly 2x4. So nominally, by name, it's 2x4. But the exact distance on that, or the exact cross section, would be 1.5 by 2.5 or 3.5. So those are the differences there. So in this equation, then the L is the actual length, and L prime is the nominal length. So you're taking the L minus L prime divided by L prime. That's basically giving you a percentage. And then the big L is the distance that you actually measured or recorded out in the field. So when we put this all together, then we can determine what our distance is. So this will step you through that. You can read those. I'm going to give you an example problem. I don't think I have it on here. So let's skip over and do a problem. So I've got a couple of problems for you guys to do for homework on this stuff too. So I want you to check it out. It's not hard to do, but it's good stuff to know, because this is the kind of stuff. Now this applies primarily to steel tape. So we're going to assume for this example that we have a steel tape that we bought, and this steel tape has an L value of what I said before, 100.02 feet, okay? And we got it calibrated, we got it standardized, and the actual distance on that is, or I'm sorry, the nominal distance rather, is this. So when we bought the steel tape, this is my nominal, this is what it's calibrated to, so that's exact. So we went out and we measured 250 feet. Now, when I say we measured, this is what we wrote down in the field, because that isn't exactly what we measured, because it's going to be different based on what this is telling me. So what we're going to do is this. We're going to calculate a correction. So the correction for incorrect length, if you recall, that said it was L minus L prime divided by L prime, and then you multiply that by the distance that you recorded in the field. So when we plug this in, notice we have 100.02 minus 100 divided by, in this case, 100. Okay, so this says actual minus nominal divided by nominal times the distance that you measured or recorded. So now think about this too. What are the units of this? Well, this unit up here is feet. That unit is feet. So feet per foot cancels, but that also has a unit of feet. So when we get that, it'll come out. So let's see what we come up with this equation. So I've got the exact distance of 100.02 feet by calibration minus what the tape says, which is 100, divided by 100 times a distance of 250 feet. So we come up with a correction that says we have plus 0.05 feet. Okay, so that says in 250 feet, we're actually longer than we should be. Okay, so to get the actual distance that we measured, we use this equation. This is what I call the true distance. L bar is your true distance. That's my true distance, is going to be equal to your nominal distance or your recorded distance, L, plus, in this case, your correction. So we simply take 250 plus 0.05, and that tells me that we actually measured a distance of that. That's what the actual distance is between 2 points. Okay. Now, understand something here that's really important, that what happens is if this number is not 1.002, let's say it was 99.99. Well, when you plug that in here, this is going to become a negative number. Well, you still just do it the same way, but this is a negative down here and it's going to subtract. So the sign here is critical. It's set up based on what this is doing. So if your actual distance is greater than your nominal distance, then you get a plus here. If your actual distance is less than that, then you get a negative. And when you plug that in, you have to plug it in negatively. All right, is everybody okay with that? So let me ask you, is this number a measure number? Is this a measurement number or a layout number? Which one is it? Or is it both?
The measure.
It would be measure, that's correct. So here's what I'm saying, and this is why this is important. If I ask you to lay out a building that was 250 feet long, what would you do here? Because remember, my steel tape is what? Is longer than it should be, right? If I go out and measure 250 feet with my steel tape, my building's not 250, it's what? 250.05. So for layout, what you do is you swap the sign. Watch how I swap the sign. If my true distance has to be exactly 250, then that tells me that this has to be true. So when I solve for what I'm measuring, what I'm doing is I'm taking that minus that, and that gets me what? 249.95. That's what I would measure out in the field to get exactly 200 with a layout problem. You guys see the difference?
Yeah.
That's an extremely important thing that I just showed you there. By the way, and just let me reference this right now. All of the problems in the book, all of those calculations for corrections, they all are for measurement purposes, not layout purposes, okay? But all you have to do on a layout problem is swap the sign. So if this is a positive for a measurement problem, it becomes a negative for a layout. And that's true with everything we do when we do these kind of problems. Does everybody get what I'm saying there now? Because I'm going to ask you how to do, you're probably going to see this on quizzes or tests or something at some point, all right? Any questions? All right, let's go on. Let's take a look at another commonly used type of thing. So what we just did, let me just back this up. This is called an incorrect length of tape type of equation. So it's pretty simple. Again, it's just your correction is equal to your true distance minus your nominal divided by your nominal times L, which is your recorded distance, okay? And then you further go in and apply that correction. So we have another one. This is another common type of mistake that you have in steel taping, is where you have temperature rather than standard. So it's primarily a systematic error as long as you know what's going on, but it has some randomness in it because temperature is not, it's variable, okay, across an area. But what this says is that temperature above or below your standard causes a change in the length of the tape. So everybody knows that if you take a piece of steel and you heat it up, it's going to get longer. And if you chill it down, it's going to get smaller. And so if you had that steel bar and you had graduated marks on or just measured the end of it, you're going to get different values of reading. So your steel tape does the same thing. Now steel is fairly stable, so it doesn't change a lot, but it changes more than you think. If you have a change of 15 degrees above or below your standard temperature, you're going to get about 1/100th of a foot change over 100 feet. So that's actually pretty much. So again, I'll say that again. 15 degrees above or below your standardizing temperature will cause 1/100th of a foot. So every 15 degrees you get more. So if I go 30 degrees, now I'm 2/100ths of a foot. Okay, you get the idea. So it's a proportional kind of thing. So this equation relays that to you and how you determine your length. So we would calculate a correction for temperature based on what we call K delta TL. Now this is, K is also sometimes in some books it's referred to as alpha. So that's referred to as your coefficient of linear expansion. And each material has its own value for coefficient of linear expansion. Steel actually is pretty high. So steel moves at a pretty good clip, whereas say concrete is going to be it's not going to change as much. Some materials change a lot more than others, and steel actually does change a lot more. T1 is the temperature at time of measurement, and that could also be considered temperature final. T itself is the standardizing temperature, and sometimes that's called TI for T initial. So we also just see that written as delta T, but you got to make sure which one you do first, okay? So it's always final minus initial. So T1 is the temperature at time of measure, final minus initial. T1 or T initial is what you call standardizing temperature, and usually that's like 68 degrees, what they call room temperature, but that really depends on the manufacturer who calibrated and manufactured that tape. So usually when you buy a steel tape, it'll have a little slip of paper in there that gives you the calibration information. So it'll tell you what the temperature was. L in this equation, the big L is the same thing as it was in the last equation. It shows us that that's the value that we measured out in the field, or we recorded. So in this case, we have to calculate a correction, and we have to apply it just like we did before. So T1 is your time at measure. T is what we're going to call standard. If you don't know what your standard is, just use 68. That's going to be pretty averaged. So K is a coefficient of linear expansion. As I said, all materials are based on their own values. So this number, that 0.000050645, that is per degree Fahrenheit per distance. So it basically just cancels out. But that is based on Fahrenheit, by the way. So if you look up metric number is going to be different because it's based on centigrade. Okay, so you got to make sure that you use the right constant. And this is the constant that we will use every time when we're doing our problems. Unless I don't think he's got any metric problems in the book. And I wouldn't throw anything metrically at you. So this number, by the way, this number for steel is derived experimentally. So there's a way they can, you can do that. You can determine how much change you've had while applying a temperature, and you can measure that and convert this into that. So that's where they get those numbers. Those are empirically derived. So this is actually a pretty easy thing to do. We used to do this all the time out in the field. I'm going to show you an example of this, how this works. And it's pretty simple process. So let me just run through an example of this. So in this case, let me, oops, crap. Hold on a minute. All right, so I want to do a problem with this, and this problem is a Fahrenheit problem. So we know that the K is given. I used to use this equation all the time out in the field, and I remembered this by using 50645. Now, if you're using metric, it's a different number, so you can look those up, but that's the only thing we'll use. So we're going to say that the standard temperature was given to us as 68 degrees Fahrenheit. Okay, so this is our standard temperature. So we go out on a really, let's say a cold day. Okay, so we go out on a cold day, not real cold, but let's say it's, let's say it is 20 degrees Fahrenheit, like it was last week. And we measured a distance of, let's say, 400 feet with our steel tape. So we want to know is, what is the actual distance? What did we actually measure? Okay. So basically, we would first calculate this. Okay. So that's K, T1. This is our T1 by T times L. And this happens to be L. So if we plug that in, so our final temperature was 20 degrees minus an initial standardizing temperature of 68. So you can see by doing that, we're going to get a negative. And that's important because that's telling us which way to apply this correction. So we have 20 minus 68. Okay, I come up with a negative 0.158. Is anybody getting that number?
Yeah.
Okay. So what that's saying is that that tape is actually contracted by 1/1600 of a foot. So if we went out and measured that distance, our actual distance is going to be slightly different. In fact, it's actually going to be a little bit more than slightly different. So what we're going to have is 400 minus that 0.158. And that gets us, we actually measured between two fixed points, 399.84. That's significantly different. So you can see that 20-degree day, I mean, that did quite a bit. Does everybody see that? Again, this type of problem, this is a measurement problem. So what would you do on a really cold day if you wanted to do a layout? What would you have to do with this? This
You would
number
add the
would,
0.158.
say that again, Jacob?
You would add the 0.158
To what?
to 400.
Well, yeah, in this case, 400, that was your layout. That's correct. So in other words, you would have to measure that as 400.16 to get actually 400. So you have to think about that when you're doing those problems, okay? So this isn't a hard thing to do. Do keep in mind though, if you have the Celsius, if you're using a Celsius problem to show you for steel, it's, let's see, it's 1, 2, 3, 4, 116, and that would be per degree Celsius, or Celsius per degree meter, I believe is what it is. So per unit actually of length. We won't probably be using this one, so don't worry about this one. This is the one that's critical for us. By the way, some in physics and other classes, they'll use alpha, so those are equivalent. Just some people use different constant values, that's all. Any questions on that? Because that's a pretty typical kind of problem. We're good on that? All right, if no problems, I got a bunch of other things on there for you to look at. Let's go back to the PowerPoint. There's all kinds of other types of errors you could have on a tape. Inconsistent pull, which means you're either pulling more pressure than you should or less pressure. That produces an error. Another big one is what they call sag. Okay, that's where if you've got it unsupported, it looks like a parabola. That can be a huge source of error, actually. And then typically what's going on is you understand that there's what we call combined corrections. So what that means is you can have a temperature correction error going on at the same time you have an incorrect length of tape going on. So basically all you do is you just take your corrections and you add them together with their algebraic signs, and then you apply that to your value. So systematic or combined corrections are easy to do. You just calculate all your corrections first, and then you add them together, and then you add it ultimately to your thing. So that's real good. That's easy to do. All right, this is out of your book. This is kind of cool, and it shows you the type of error that would be associated with steel taping, whether it's an instrumental, natural, or personal, whether it's systematic or random, and how much it departs from 100th and 100 feet. So again, there's your, like, if you are out 15 degrees or above or below, you're 100th of a foot out. If your pull is 15 pounds over or under your standardizing temperature, you're 100th of a foot out. Okay, so that's kind of what that's showing you, all right? Tape not level is interesting. So this says that if you are out of level by 1.4 feet in 100 feet, you're only throwing that tape out by 100th horizontally. So that's kind of a nice one. I do want to mention something though before we get done. We're almost done here. One more thing, because we're going to be utilizing this again, actually in other pieces of this class. If you are on a slope, okay, slope is pretty easy to handle if you know the slope. So let me relate this two things that you might see. Slope can be expressed typically one of several ways. Okay, so I'm gonna. Okay, one way is to do what's called a percent grade. Oops. So we can see that expressed as percent grade, which is defining this. Or we could also define it as an angle off of the horizontal, which we would call theta. So some people think these kind of are the same thing, but they're actually absolutely not. So if I say that I have a 5% grade, that does not mean that this is 5 degrees, okay? Does anybody think that? I hope not. Can anybody tell me what this angle actually would be? Or what do we mean when we say 5%? What does that mean? What does 5% mean when you're talking about grade, which would be things like highways, parking lots, pavement? What does that mean, 5%? Nobody knows that?
I mean, the slope can't be greater than 5%. Like for
Well, I'm
highways, I
not
think
saying that I'm not saying it's a maximum. I'm just saying if I say to you that the slope is 5%, what is that saying to you? You never been down, you ever driven down the expressway and it says trucks use glow gear, next grades are 5% or 6%? Anybody ever seen
Well,
that?
yeah, that's definitely saying you're going downhill. It's going to be a big hill.
But what does it mean? What does 6% mean? Yeah, it definitely means it's steep, right? Yeah. You don't want to be in a truck that doesn't have brakes. But what does 6% mean? It means that for every 100 feet you travel horizontally, you're rising or falling 5 feet. So what that's saying, if we look at this triangle here at a 5% grade, that if the horizontal is 100 feet, we're rising or falling 5 feet. Now, that doesn't maybe sound like a whole lot, but if you think about this, think about any interstate highway that you've ever driven on, and they max out at 6%. So you can't have interstates higher than 6%. Only occasionally will you have that. I've seen a couple out west that maybe go to 7, and in West Virginia you have a couple, but most of them are maxed by law at 6%. That's steep, okay? And this, by the way, doesn't mean necessarily feet. It could be 5 inches and 100 inches or 5 meters and 100 meters. So it's basically a unitless number. So
What is the
when
cut
you
in the hill?
go ahead, what's the cut?
Yeah,
What is
what's
it?
the grade of the cut in the hill?
Well, it has to be at 6% or less. So even though it might seem like that, I don't think we have anything higher than 6% around here. I'm not 100% sure on that. But by law, by code, most interstates max out at 6% because anything higher than that is hard for a truck to pull. Okay. And also, of course, it's pretty dangerous when you start going down hills, right? Okay.
There's a
So
9% grade right by my house.
yeah, but is it an interstate?
No, I don't think so. It's close
No.
to
Okay.
128 in Ross.
Right. See, that's not an interstate. Okay. So you have when you talk a federal government interstate highway, they max out. Most of the interstate system is about 6%. You will occasionally, like I said, you'll see some 70 something through West Virginia goes to a little bit higher. And I was out west, you go over the mountains out west and they got a little bit higher, but they're not much higher than 6%.
And then, like, I just came back in Colorado. I remember driving through the mountains on their grades. They always have truck runoffs.
Mm-hmm.
Or if a truck's brakes go off,
Yep.
is there a certain percent that those have to be on too then? Or
Well, they do because they have to have enough room to put them in, but they also, they have to have enough because what that does is that dissipates the energy. So they have to have enough room for the runoff to be able to make sure that a truck, if it's coming down without brakes, it's going to make it into that. But yeah, they have those quite a bit out west. You don't
I
see
remember
those.
there's one by Estes Park that looks like a half pipe where it goes like straight down and then the truck runoff goes like almost straight up. It's
Yep.
crazy.
Yep. Yeah, because they probably didn't have enough room to make it real long, so they just
Yeah.
did it that way, kind of thing. Yeah, that's part of it. So here's my other question before we get out, because you're going to have questions in the book that you're going to see this. So how do we convert a 5% grade into a theta with respect to horizontal? Can everybody tell me? Well, if this is 5 feet and 100 feet, another way of saying that is what? Rise over run, right? So what we're saying is this angle here, theta, is related to these two guys by something called a tangent. So if you took the tangent of 5 over 10, we could convert that, take the arctangent of 5 over 10. Let's see what we come up with. Anybody get a number? Turns out to be like 2 degrees, 51 minutes and 45 seconds.
Yeah, that's correct.
So that doesn't sound very steep either, does it? Trust me, it is though. Okay, that's like I said, that's considered. If you looked at 6%, that angle is going to be a little bit steeper, but that's max. So the reason I'm showing you this is because there are some problems here that we're going to be working through. And out of chapter 13, there's a couple I want you to look at. They're going to be talking about giving you either percent or this. So you need to be able to handle that, okay? And we're going to see this a lot because we're going to start getting into highways and pipelines and that kind of stuff. And most of that stuff is expressed this way. Also, when you look at a set of plans, almost everything is what they call percent grade. You never really see it expressed this way too much. But sometimes it's easier to convert this to this, and then I can use things like sine and cosine, okay? So those are just some things to think about. All right, questions? We covered a lot of good stuff today. I didn't get through everything here. You guys can read through this. We're going to talk about I'll probably pick up with some of this distance stuff like next week to finish it off, but primarily we're going to look at starting to do radial stakeout stuff next week. So the big deal today is let's get ourselves going on getting that lab done, and I'll plan on seeing everybody on Thursday. Yeah, look for your grades to be posted. I'll probably get them posted tonight or tomorrow morning, one of the two. And if you haven't taken that test, you better contact me, or you better do it, because it times out tonight at midnight. Okay. Does anybody have any questions?
There's 2 test ones in our my grades on Blackberry.
That's only for, yeah, the test one is for the guys that haven't taken it yet. Okay. So those that'll disappear as soon as I get grades. Okay. But your other one, yeah, the other column that is the one that you'll be looking for. That'll be filled in with the number. Okay. And I'll bring those with me on Thursday. We won't have a lot of time to look at them, but I'll give them to you, and then you can look them over, and then we'll take it from there. Okay. Any other questions? All right. Well, I'll plan on seeing everybody then on Thursday. And if you have any questions between now and then, just make sure you contact me. Okay. Talk to everybody later.